Okay, let's see. Yeah, this looks like it's working better. I'm not trying to make you dizzy. I'm just trying to figure out if this is working. And, now, how do I write on it? Okay. I can write on it. Good. I can write on it. My finger isn't writing on it. All right, temperature. We just want to get off a couple of these things. You don't need your periodic tables, but if you did look at the back of your periodic table later, don't worry about it right now, you're going to have these equations on there. It shows you how to convert down in here somewhere. Yeah, temperature. It shows you the equations. So you'll have access to this, but to just Mark, could you turn this off again, please? To just get this in mind right now. So Fahrenheit is what we're using here in the United States. So the weatherman's telling you it might be high of 80 today. Fahrenheit. High of 80 degrees Fahrenheit. In the laboratory, you pull out a thermometer, it's going to be in Celsius. And so let's compare these two. I've got a lot on here right now, but let's just look at these two. And the thing that I'd like you to appreciate is they have two very fixed reference points, centigrade and Fahrenheit. Their reference points are something that we can easily get at no matter where we are in the world. Freezing point of water. Water, that is a physical property of water, where it freezes. All right? On the Celsius scale, it has been marked at 0 degrees centigrade. So the centigrade scale is indexing off of the freezing point of water. And it goes up to the boiling point of water, 100 degrees centigrade. There's where you get centigrade, 100 grades. There are 100 degrees. So this is also called the centigrade temperature scale, Celsius or centigrade. And I probably use centigrade or just abbreviated C. All right? Centigrade. Again, along with the metric system, it's a power of 10 based system, 10 squared. There's 100 degrees from the freezing point of water, freezing point, to the boiling point of water is 100 degrees. Now, the Fahrenheit scale, those are still two important reference points, and I mean that's just really how you would calibrate a thermometer. You would put it down into ice water, ice and water. It's at the freezing point of water. If it got any colder, more of the water would turn to ice. The temperature wouldn't drop. Got any warmer, some of the ice would melt. The temperature would not go up. Some of the ice would melt. So it's going to just stay right there at 0 until all the ice melts, and then the water will start warming up. So that is a good reference point. And then likewise, when you boil an egg, you put the egg on the stove and you turn the heat up high and it boils. What's it do? It gets up to 100 degrees centigrade and stays right there. That's why you can do a 3-minute egg. No matter where you are, just boil the water for 3 minutes or put your egg in boiling water for 3 minutes. You got a 3-minute egg or a hard-boiled egg, whatever you want to do. So these are reference points, and that's been used for the thermometer. But notice that from the freezing point to the boiling point are 180 Fahrenheit degrees. Okay? So the same reference point, freezing point, boiling point, there's 100 centigrade degrees. There are 180 Fahrenheit degrees. So look at what you get. There are 180 Fahrenheits per 100 centigrades. So there is 1.8 degrees Fahrenheit per degree centigrade. And if you look on this periodic, or not the periodic table, but on the back of the periodic table, there is a factor of 1.8 in the equations. That's where that factor is coming from. So if we have a centigrade degree and we want to convert it into Fahrenheit, we have to multiply that by 1.8. Why? Because there's 1.8 Fahrenheits per centigrade. And we have to add this to it, 32. Why? Because the Fahrenheit scale starts at 32, doesn't start at 0. So we have to compensate for the fact that the two temperature scales start at two different places. And you end up with that equation. Okay? So that's just not some sort of arbitrary equation. You could actually look at those two temperature scales and derive it. So let's do a calculation. Let's say you're down in Brazil and the weatherman says today it's going to be 28 degrees centigrade. So what is that? Do you need a jacket or do you need a swimming suit? Figure it out. It's 28 degrees centigrade. Convert that. Well, let's do one together. So we have 1.8 times 28 degrees centigrade plus 32. Do that. I've encouraged you, I've said it before, but I want to encourage you to always bring the same calculator. Have a calculator. I mean, right now it doesn't matter. You can do this on your cell phone. But on an exam, you have to use your calculator. So get, your calculator's your friend. Get familiar with it, how it uses, how you enter numbers, how it works. And the scientific calculator and the TI 30s, which are also scientific calculators, function a little bit differently. So what do we get? What is it? Okay. And if we did, we're going to talk about dimensional analysis, but if we did it here, remember there's 1.8 degrees Fahrenheit per degree centigrade times your 28 degrees centigrade. My degrees centigrade are crossing out. This is converting over to degrees Fahrenheit. That's a little picture, little window into dimensional analysis. Dimensional analysis says the units on a number are as important as the number. Okay, so yeah, we're going to just use the number 1.8 there. We won't worry about labeling it like this. We don't need to worry about labeling it like this in this particular case. But I just want you to know that's just not an arbitrary number. Another way of writing this equation is this, that Fahrenheit equals 9/5 centigrade plus 32. But what is? Divide 9 by 5. 9 divided by 5 equals 1.8. Okay? So there's nothing different about those two ways of writing the equation. Sometimes it's shown up that way as 9/5 C plus 32 or 1.8 C plus 32. And then just quickly, you'll see this on the back there. Let's start with that equation again. And I'm going to, today I'm going to do some simple algebra, basic algebra, but we're going to be using basic algebra the rest of the semester when we work with equations. And just to point out, if you have an equation, remember, if you have an equation, you can do anything you want to this equation as long as you do the same thing to the other side of the equation, right? And it'll stay equal. So I can take that equation and subtract 32 from it. If I subtract 32 from that side, I need to subtract 32 from the other side. And I maintain my equality. So I have F minus 32 equals 1.8 C. Now, I can take this equation and divide this side of the equation by 1.8, which means I have to divide that side of the equation by 1.8. Now, why do I want to do that? I want to get rid of the 1.8 in front of the C. 1.8 divided by 1.8 is 1. So now I have C equals F minus 32 divided by 1.8. And what do I have? I have the second equation. How to convert Fahrenheit into centigrade. So, all right, let's say today is going to be a high of 85 degrees Fahrenheit. What is that going to be in centigrade? Now, let me just point out one thing that people sometimes make an error of. You have to subtract the 32 from your Fahrenheit before you divide by 1.8. So think of that as a package deal. You got to do the numerator first and then divide by 1.8. So if you were talking to someone from Brazil or Europe and they said, well, how hot is that going to be? How hot is that? In centigrade. 29 what?
0.4.
And label it. All right? The full answer is 29.4 degrees centigrade. It's not just a number. It's a number and a unit. From now on, everything I see, I want to see a unit after it. There are very few numbers. The only time there's a unitless number in any of our calculations is when there's just a comparison. Like how many times heavier is this than that? You say 10. It doesn't have a unit. It's 10 times heavier. If it weighs a ton, then 10 times a ton, that's 10 tons. It's just a comparison, but there's very few units in science, or very few parameters in science that are unitless. Specific gravity is one where you're just comparing the gravity, the density of one item to the density of another item. It's a comparison. But other than that, numbers will usually have units. Now, I think I mentioned to you when I was flying back, it said the outside temperature was minus 54 degrees Fahrenheit. I think they were, trying to make you feel very thankful for your seat, and that was at room temperature. We were flying at 32,000, almost 33,000 feet, and outside the airplane was minus 54 degrees Fahrenheit. So convert that to centigrade. What did we get? Now this is a little bit tricky. We got a negative Fahrenheit temperature. Eight. And I would like you to round like that now, since we've talked about rounding. You see 47.77777, round it to, so it's negative 47.8 degrees centigrade. Yes, and how do we get that? Well, so you got minus 54 minus 32. divided by 1.8. And what did that end up being? Minus 86?
Yes.
All right? So if you take minus 54 and subtract 32 from it, you're down to minus 86. Then you divide that, you divide that by 1.8, and you get this temperature here. Good. All right. Now let me try to find density slides. Where are the density slides? I'm bouncing around a little bit in here. Where is my... Oh, I'm sorry. Oh, density. There we go. We're getting into density. Oh, I forgot to mention, where was that temperature? Where'd my temperature slides go? Again, I should have printed these out in front of me. Okay. We overlooked Kelvin here. Kelvin. You go in the lab, you're not going to find, well, at least in our labs, typically you will not find a Kelvin thermometer. I guess if we were in a physics lab or people were looking at really low temperatures, working with liquid nitrogen, things like that, they might have Kelvin thermometers. But let's just look at these real quickly. And the Newton thing may go into conversions from Kelvin to Fahrenheit. I am not going to give you those kind of conversions. I expect you to convert centigrade to Fahrenheit, Fahrenheit to centigrade, and I expect you to be able to convert Kelvin to centigrade and centigrade to Kelvin. Can you convert Kelvin to Fahrenheit? Yes, but practically speaking, this is where we live. We live with the weatherman telling us stuff in Fahrenheit, and we need to know it in centigrade. We, in the module on gases, we're going to use this temperature scale routinely. When we get to the ideal gas law on gases, we'll be talking about temperature in Kelvin. So what is Kelvin? Kelvin is also referred to as the absolute temperature scale. So sometimes you'll say, well, what is that in absolute temperature? What they mean is Kelvin. And why do they talk about it that way? Because Kelvin starts at 0, theoretical absolute 0 Kelvin. Nothing can get any colder than that. That's a theoretical limit. You can think of, well, can't things just kind of get as hot as they can get? Like the sun, how hot is the sun? Can it get any hotter than the sun? There doesn't seem to be any limit on how hot things can get, but there is a limit on how cold they can get. Because what 0 Kelvin is equivalent to is 0 energy. When you get down to 0 Kelvin, when you get down to that cold, whatever it is that's that cold, has no energy. 0. So you can't get below that. You can't get below 0 energy. They will talk theoretically about negative energy and all that sort of thing, but those are mathematical, physical constructs to try to explain things they can't explain. But you can't get any less than no energy. And so that's where Kelvin begins, at 0 energy. It gets up at the freezing point of water is 273 degrees Kelvin. And the boiling point of water is 373 Kelvin. They don't usually use the degree, they just use the K. 273 Kelvin, 373 Kelvin. So what you can see right there is from the freezing point to the boiling point of water is 100 K. And there are 100 degrees C between the freezing point and the boiling point of water, right? We saw that already. There's 100 C from freezing point to boiling point. There's 100 K. There's 100 degrees if you go from the freezing point to the boiling point in Kelvin. So the beauty of that is that a Kelvin degree and a centigrade degree are of the same magnitude. You go up 1 degree centigrade, you've gone up 1 degree Kelvin. So what that ends up with is a fairly simple equation, is that Kelvin equals centigrade plus 273. So, for example, 0 degrees Kelvin, or excuse me, 0 degrees centigrade plus 273 is going to be 273 Kelvin. So the conversion is pretty simple. We just have to add or subtract 273 from the number, add it to centigrade, subtract it from Kelvin, and you've converted between the two. All right, so these are pretty straightforward. And all of those equations are back there. It says 273.14, excuse me, 273.15. That would have 5 significant figures in it. To 3 significant figures, this is a good enough number. All right, yes?
What if when you say like add 12 Kelvin to 45 degrees Celsius? Like how would you convert it?
Okay, so well, that would not be a question you'd be asked. You're not.
It was.
It was in Newton.
Yeah, it said add 16 Kelvin to like
40
degrees Celsius or something, and I was like,
okay. I mean, the questions should be convert. Yeah, it should be convert 45 centigrade to Kelvin. That would be a legitimate question. Convert 45 degrees centigrade to Kelvin.
yeah, I mean that one was on there too, but the one that I had was like.
So add 16 degrees Kelvin to 45. I don't know what they're asking. That's
I tried figuring it out.
it's kind of a bogus. I mean, you could just take 45 plus 16.
And that would, okay, I thought you had to like convert it.
But you see that what's got me is 16 degrees Kelvin. Kelvin starts down here at 0, so 16 degree Kelvin is down here, and 45 degrees centigrade is up there. There's no relationship between those two temperatures.
So on that question, there's.
Yeah, that's a bogus question. If you got it wrong, come in and show me the question. You did?
Yeah, well, I don't know.
If some things like that happen, feel free to come into my office. I'll pull that assignment up and we'll look at it. And if it's what I would say a dumb question or a kind of a bogus question, I will be able to understand what you're asking better when I can actually see the question. But I'll correct it if I think, geez, I don't know how to answer this question either. It's kind of a stupid question. We'll just throw it out. Okay? Okay, now let me try to find my density again. Where was it? Was it below here? Density, there we go. Okay, let's talk about density. I'm bouncing around a little bit. We talked about the 3 basic things we measure: mass, how heavy something is, grams, volume, how much space it occupies, liters, milliliters, ounces, quarts. Those are volume measurements. And we talked about distance, inches, feet, centimeters, meters. This is a meter. It's a meter. This is not a yardstick, okay? On the back, we got inches, but a yardstick would start at 36 inches. This one goes to 39 and some inches because it is a meter stick. It's 1 meter long. It's 100 centimeters. It's 1,000 millimeters. All the little black lines on there are a millimeter. So that's a meter stick. Okay, so those are your three, and then temperature we talked about today. That's another basic unit. That's not length, that's not mass, it's not volume. That's what's the temperature of this thing. And it has some relationship to the energy that material has in it. So now, what are we doing with density? We're taking two of those fundamental measurements and looking at the relationship between them, mass and volume. Density is the ratio of the mass to the volume, or mass per unit volume. That's the density. And materials vary in their densities. I love this picture because it has a whole bunch of things right here that all have different densities. Here's liquid mercury. Floating on top of it is a metal brass nut right here, floating on the mercury. So what's that say? That says that the mercury is much more dense than that brass nut. Actually, much more. We'll look at some numbers here in a second. All of this is in water. These both have sank to the bottom of the water. So here's water. And then here is cork. It could be a chunk of wood. And then even above that is what? Air, gas, which also has a density, but a very low density. That's why, you swimming underwater, you're scuba diving, and you're exhaling, and all that gas is just rising to the top real quickly. It's low density. It's forming this bubble of low density gas, and it's rising up to the top of the liquid, bubbling out of the liquid. And this here is about 13.6 grams per cubic centimeter. This, I don't know, it's around 6. Don't quote me. Brass might be about 6 grams per cubic centimeter. Water is a reference point. We just used it for freezing point and boiling point of water. Water is used as a reference over and over and over again for all kinds of parameters and density. 1 gram per cubic centimeter. Some of these units are actually wrapped around the properties of water. So it really turns out this is what water comes down to, 1 gram per cubic centimeter, and then cork might be about 0.7 grams per cubic centimeter. So you see, as the density increases, they're coming to the top of this scheme right here. And then air is, air above it is, something, couple decimal points, and then grams per cubic centimeter. But notice that the units, we've got a mass here, grams, and we have a volume unit, cubic centimeters, or milliliters. The cc right here stands for cubic centimeter. Motorcycles will, a Kawasaki 750, it's got a 750 cubic centimeter displacement in the pistons in the engine of that motorcycle. A Honda 1500 has got a 1500 cc engine, cubic centimeter. This cc used to be used in hospitals, like it'd say give 1 cc or 8 cc's. They've eliminated that. Most hospitals, they said we're not using that anymore. They will say, I think they will say milliliters or milliliters. Why did they eliminate that? Because this and this got confused too often. So you'd say, oh, they need 1 cc. And what were people getting? 100. It was leading to mistakes because of bad penmanship. Are doctors noted for their good penmanship? No. So they've eliminated that. I don't know if it's by law or by decision, but your very good medical places, and we're not using that abbreviation anymore. It has gotten too confused. It's too ambiguous. People are left thinking, I wonder what he meant. I mean, you can see, you write a couple C's real quickly, and you can't tell whether they're a C or a 0.
That makes sense. The charges came out just like that with the things that were just banned, and the abbreviations they can't use anymore and everything like that because all the mistakes they were.
Was this in the military?
No, it was this is when I was in the hospital. There's a chart for everyone to see.
And they said, don't use this abbreviation?
Yeah, and so there was a huge list of all the things that people were getting mixed up with. So they switched it all around.
Okay.
So new acronyms and stuff.
There's still in some blocks that will say CC, but we'll have to ask them again, and it's like, yeah, me and one.
Okay. So when you do see that, you have to verify, confirm what they meant. Yeah. Okay. All right. But what you will see in here are this and this very, interchangeably, and actually 1 cubic centimeter. I was pointing that out over here. 1,000 cubic centimeters is 1,000 milliliters is a liter. So what does that mean? If 1,000 cubic centimeters is 1,000 milliliters, then obviously 1 cubic centimeter is equivalent to 1 milliliter. And what you'll see sometimes is in solids. In solids, they might express it in cubic centimeters, and when you revert over to liquids, you might be seeing it as 1 gram per milliliter. A liquid we can measure in a graduated cylinder, and it's usually got milliliters on it. Okay, so let's. So we've got this equation. Density equals mass over volume. And this is fairly basic. This is review, but let's just kind of walk through a couple of these and lean hard on our simple algebra to solve some of these problems. This is the equation that defines density. So when you have a problem, let me show you how to deal with a word problem. You're going to have a lot of word problems. You're going to have them in gas laws and different things like that. So let's see. This is a simple one, so let's just kind of go through what should you do. Don't rush through these things. Read the problem. A piece of silver weighs 194.3 grams and occupies a volume of 17.5 milliliters. Let's put the milliliters over here. What is the density of this silver? Okay, so read the problem. Now, analyze the problem. What does it want me to do? It wants me to calculate density. Density. That's the question. 194.3 grams. What is that parameter? What is it? Mass. So sometimes when I'm doing a problem, if it's complicated, I'll actually label it. That's the mass. It occupies a volume of 17.5 milliliters. It's telling us that's the volume. Right? So, plug those things with their units right into the defining equation. All right? Set it up. Set it up like that. Don't touch your calculator until you're this far. Don't touch that dial. Okay, don't touch the calculator until you're this far. You got it all set up. You've read the problem, you've analyzed the problem, you've figured out what these numbers actually are and where they should go in this equation. And pull the units in with them. Now pick up your calculator and do the calculation. And of course you're going to need to round the number off. And you're going to round it off to how many significant figures? 3. This 17.5 has 3 significant figures. And that's going to limit the answer. So what's the answer? 11.1 what?
Grams over milliliter.
Grams per milliliter. Okay? So 11.1 is partial credit. 11.1 grams per milliliter is full credit. Got to have the number and the units and the right significant figures. Okay, let's do one more together, and then we'll do, I think there's a third one, and you can do it on your own. Okay, lithium is the least dense metal known with a density of 0.53 grams per cubic centimeter. I'm sorry these units got separated from the numbers. What is the volume occupied by 123 grams of lithium? Okay, we read the problem once. Now analyze the problem. Lithium is the least dense metal known with a density of, this is density, 0.53 grams per cubic centimeter. What is the volume? So what I would do is volume, what is the volume? That is the unknown. It's occupied by 123 grams. That's the mass. Okay, this is a density problem. So when I solve a problem, and what I'm doing with you is I'm showing you how I solve a problem. You come into the office hour and sit down and say, Mr. Rack, here's this problem. How do we solve this problem? I'm going to work through my steps methodically, systematically. I will not touch my calculator until I have analyzed it, I've looked at the equation, I've rearranged the equation, and I have the numbers in the equation the way I want them. Then I pick up the calculator. You are not going after a number. You are going after an accurate answer. All right? You want the answer, not a number. You want the whole number, the whole answer. So I go back to what defines density. D equals m over v. I see that v is the unknown. So I want to get v all by itself. Before I put any numbers in here, I'm going to rearrange this equation algebraically. So I'm going to multiply this side of the equation by v, and I'm going to multiply that side of the equation by v. And I get v times d equals m. I'm not there yet. I want v all by itself. So I'm going to divide that side of the equation by d, which means I have to divide that side of the equation by d. And I end up with v equals m over d. Now I'm ready to do the problem. Put the mass in here. Put the density in there. Okay, now I'm going to insert one other step here, dimensional analysis. So all of a sudden here the numbers are going to, I'm going to ignore the numbers. They're going to be invisible. So what I have here is grams divided by grams per cubic centimeter. This is the dimensional analysis. I'm in analyzing the dimensions. Now, if I had a problem that said I had 1 divided by a fraction, how would I get rid of that fraction? What can I do with the 1/2? Can I invert and multiply? This is equal to 1 times 2 over 1, right? Which is 2. Well, this is going to be equal to grams times cubic centimeters per gram. I'm inverting that fraction. This is a fraction. I'm going to invert it and multiply, and grams cross out. Okay, I've gotten a little bit ahead of myself because we haven't really introduced dimensional analysis, but I'm introducing it right here. Dimensional analysis says you can treat units like they are numbers. You can treat them just like they are numbers. We'll go into it a little bit more in a second. But that tells me enough that my units for my answer here are going to be cubic centimeters. Does that match a volume? Is that a volume unit? Yes. If I come out with a unit here that is meters, now I can't here, I don't have any meters in here, or if I came out with grams squared per cubic centimeter and I scratched my head and I thought, I don't know what that is. I don't even know what that is. I'd say, well, something's wrong. I might not have this set up right. So before I even bother figuring out what that number is, I make sure that my equation is getting me to a proper unit for this parameter. All right? Now, it's taken a long time to explain this, and you're going to say, I don't have enough time to do problems like that. I got to do them a lot faster. But do them slowly this way through these simple problems, and you'll get faster and faster and faster at it, and you'll be more accurate. Okay? You don't want a method that gets you the answer 50% of the time, do you? You're heading on into the medical, into the health profession. You can't live with, and your patients can't live with, a 50% accuracy rate. Okay? You need methods that are going to lead you to the right answer, or are going to stop you, make you slow down when things aren't adding up. Something isn't adding up. So this is a way to double check. So now, do the calculation. Technically speaking, we only got 2 significant figures there in our density, don't we?
Do we round down?
Well, you round according to rounding rules. So if the third number is less than 5, yeah, you don't round down. You don't. You would.
Like since it's 232.
So we're going to say 230. Yeah. So round down. 230 cubic centimeters. It came out to be 232.07 something da. So we would round that to 230 cubic centimeters. Okay. Okay, now let me see your thing here. Oh, I don't have a good density problem here. Let's do one other. Solve this problem. What is the mass of 29.3? What is the mass of a metal that is 29.3 cubic centimeters and has a density of 4.57 grams per cubic centimeter. All right, so solve that problem using everything I just told you right now. Read the problem, analyze the problem, use the equation, rearrange the equation, evaluate the units, and then calculate the answer. Yeah, okay, we'll talk about that. Yeah, the triangle is...
Is it M over V times D?
Okay, now here's how you figure out, here's how you remember that triangle. Okay, here's the equation, right? So just put that into a triangle.
Okay. Oh, okay.
That's the triangle. You see how that
Yeah.
looks like that?
Okay. Thank you.
Yeah. Let me get attendance real quickly while I'm working on that. Kaylee. Oh, wait a minute. Oh, I got the wrong class. Where is it? Okay, Allie. Andreas. Chloe.
Here.
Viviana. Luke.
Yes.
Mark.
Here.
Michelle.
Here.
Jean. Natalie.
Here.
Melody.
Here.
Christy. Ashley. Ashley.
I'm yellow.
Ashley Gillick.
She's on here.
Amanda.
Here.
Joel. Alejandra.
Here.
Daniel. Ashley.
Yellow.
Okay. Tasneem.
Here.
KK.
Here.
Adrian.
Here.
Shantae.
Here.
Hannah.
Here.
T.
Here.
And Egypt. Okay. All right, so you would start here. And you can see that M is the unknown. And all you got to do is multiply both sides by V. So M is going to equal dV. All right, because M is in the numerator, all you got to do is get the V over to the other side of the equation, and you do that by multiplying by V to get the V out of the denominator. You multiply the other side. So then you have a density of 4.57 grams per cubic centimeter. And you're going to multiply that by 29.3 cubic centimeters. Okay, now the dimensional analysis. What do you have? You have grams per cubic centimeter times cubic centimeters. And you know that your unit out here is going to be grams. Is that okay with you? Since you're calculating a mass, yeah, that's okay. That looks good. So now do your calculation. So what is the mass of that metal going to be? Yeah, 3 significant figures.
134.
Is that good? Was there any rounding involved there?
Yes.
Okay.
133.
134. Okay, let me just go one more step here. When I first started doing problems a long time ago, that's kind of how I set them up. More recently, the way I'm setting these things up is I have 4.57 grams per cubic centimeter, and I'm multiplying by 29.3 cubic centimeters. All right? Why do I do it that way? Well, I'm telling you, dimensional analysis is a powerful tool. So keeping track of where a unit is it above or below the line, is really important. So if I set it up this way, I can clearly see that I have a cubic centimeter in the numerator, I have cubic centimeters in the denominator, and my answer is going to be grams. When we get into Module 7, into molar masses, converting of molar masses to number of moles, stoichiometry, mass calculations based on a balanced chemical equation, we're going to have 5 or 6 numbers sitting next to each other, and we're going to have to be keeping track of where all the units are and what the final unit is going to be. And this is the way you'll start seeing me putting a lot of problems on the board. It's like this. So, you know, I'd have it set up, it'd look a little prettier than that. It'll just like this. Okay, so there's nothing down here. This is 29.3 cubic centimeters. There's nothing down here. But it lets me clearly see my units and where they are in relationship to one another. Okay, Mark, can you turn this light back on a second? So dimensional analysis, let's take this example right here. There is a slide that shows this. Before we got started this morning, about 5 minutes to 8, I actually took the meter stick and measured out 10 centimeters right here. So from 0 to 10, I measured out another 10 centimeters here, another 10 centimeters there. Why did I do all that? So a cube that is 10 centimeters by 10 centimeters by 10 centimeters is a liter. That is the definition of a liter. A liter is defined that way. The volume of space that is 10 centimeters by 10 centimeters by 10 centimeters is a liter. Now what is that? 10 centimeters times 10 centimeters. So volume, the equation for volume is length times width times height, right? So length times width times height. That's the equation for volume. So let's take that. We got 10 centimeters by 10 centimeters by 10 centimeters. We multiply the numbers, is 10 times 10 times 10. That's 1,000. But centimeter times centimeter times centimeter is a cubic centimeter. We could measure this room, we could measure the floor in this room in meters, and we would count meters times meters is going to be square meters. That's area. And then we could measure the height of the room and multiply it by however many meters high it is, and we would have cubic meters. All right, then we get to a volume. So centimeters squared is an area, centimeters cubed is a volume. And so this calculation right here is 1,000, that's the number. Cubic centimeter is the unit. It's not 1,000 centimeters. It's 1,000 cubic centimeters. All right, a centimeter is a distance, but a cubic centimeter is a volume. And so if here is 1 centimeter, there's 1 centimeter, and you come back 1 centimeter, you can see there are 1,000 of those little cubes in that cube. You know, there's 10 of them along here, they're 10 high, they're 10 deep. You got 1,000 of them in there. So that's 1,000 cubic centimeters. That's 1,000 milliliters. That is 1 liter. And you can see that, 10 centimeters equals 1 decimeter, 1/10 of a meter. That's what a decimeter is. So this is also 1 decimeter cubed. Because this is 1 decimeter, this is 1 decimeter, and this is 1 decimeter. So 1 decimeter times 1 decimeter times 1 decimeter, 1 cubic decimeter. These things are the most important things to remember right here. A liter is 1,000 milliliters, which is 1,000 cubic centimeters, and those are equivalents. You can interchange cubic centimeter with milliliter. Those are interchangeable units because they are equivalent to one another. If you look at Canvas homepage, it should look a lot like this right now. Because what I did, I went in there and took snipped that out and printed it. So this is kind of your to-do list for tonight, today, and the coming week. So let's talk a little bit about what you should do, and then you're going to see something at the bottom. You can say, I wonder what that is. And I'll tell you. Okay? So, so for today, you have scientific notation. You got these quizzes. The quizzes are showing first because those are hard dates. Okay? Those are due dates in there. So Canvas is telling you, hey, this is due by 10 o'clock tonight. I think from now on, they're going to probably show up as midnight, 11:59 p.m. These won't today. I set those a while ago, but I'm going to let you figure out what time you want to go to bed. I'm going to try to figure out what time you need to go to bed. All right? And on a selfish note, it defaults to 11:59 p.m. when I go in to do this. So I have to go in and change all those times. And there's too many assignments to keep changing all these things. So it shows the quizzes. The homework assignments are underneath. I sent out a note a while ago. I told you what I would do if I was sitting in your seat. What I would do is I would pick one of these homework assignments. Let's say it's density. I would do that homework assignment, and then I would go do the quiz. All right? Don't think, I mean, you can do it however you want to. You can do all the homework assignments and then go in and start doing all the quizzes. But it's going to all just, so do a homework assignment, go do the quiz. And you'll get a little bit of a feedback as to whether you kind of understood that. And I don't know how Newton works. If you open up the quiz, can you kind of come back and do it again later?
Yeah.
So you could look at it and go, I don't think I understood that homework assignment. I don't even know what they're asking. So you go back into the homework assignment. But if you do it that way, you're knocking off two things. And you are setting yourself up to understand how to do the quiz. And then just work down through it. And obviously you need, this is like eating. You eat 3 times a day, maybe 4, I don't know how often you eat. But you don't just say, oh, I'll eat at 8 in the morning and then I'm going to forget about food the rest of the day. You nibble away, you eat, right? So these, you need to chew on these things on a daily or regular basis and knock them off. And then I just set up the ones for next week, which gets into the chemical reaction, classifying them, identifying what is an acid-base or an oxidation reduction or precipitation reaction, how to balance chemical equations. And there are quizzes, and it didn't even show the homework assignment. Okay, now, so concentrate on ones for today, and then after that, start in on modules, what is it, module 6 is the next module? Okay, now look at the bottom one. Sci-Tober Mole Day Festival, worth 50 points, potential value 150 points. So it's going to go in as a 50-point assignment, but if you make 150 points on it, you're going to get 100 points extra. Okay, what do you do for that? So that is Tuesday, October 23rd, and it's going to be like from 10 to 3, and Wednesday, October 24th, from 10 to 3. This is going to be out there. We're going to have class. We're not canceling class. We're having class. But next week, Tuesday, October, what is that going to be? 16th. And Wednesday, October 18th, from about 9:30 to 10:30.
You mean the 17th?
Oh, this is Thursday. I'm looking at our class dates here. Class dates. So right after class, next week, we're going to label water bottles. So we're going to rip the labels off these bottles, and I'm going to give the class every one of these bottles, but we're going to convert them into mole water. It's not going to be 500 milliliters of water. It's going to be how many moles of water is in that bottle of water. And we're going to give them away on Sci-Tober. So there are going to be some activities. Let me say one is going to be labeling water bottles. One is going to be manning or womaning the tables out there for like 1 hour. Equals 50 points. Equals 50 points. So there's things you can do. There's a couple things that I just need one person. Like if someone wants to go out to HEB and get helium balloons, there's kind of one-off deals. There'll be other things I'll add to this list, and I'll just say these are worth a certain amount of points. And then I'll be keeping track of this. We'll tally this on a list, and I'll punch those points into that assignment when we're all done with this. On the 24th, 25th, I'll look at who did what, when, how long, and pick all the points, all right? So if you are not available during these times, then you need to find some time to come in and label water bottles, do something. All right? All right. There's your checklist. Go for it. Get these all done by 10 o'clock tonight.